In the previous lecture, we saw how two solids, when they come in contact, apply frictional force on each other and how that affects their motion. In this lecture, we are going to look at another kind of frictional force when a body moves through a fluid or gas. You are well familiar from Stokes' law that when a spherical body of radius a moves through a gas or fluid at speed v, it's moving with speed v, then there is a force on it due to viscosity, which is F equals minus 6 pi a eta v. This minus sign denotes that the force is opposite to its direction of motion. Eta is the viscosity coefficient. This is one example of the drag force that any body moving through a fluid or gas experiences. Of course, this is the lowest order force. We may have forces which are proportional to V, which are proportional to V square, or higher powers. These forces oppose the motion, and in this lecture we are going to look at how to deal with these forces when they are included in the motion of a particle. The simplest one, as I said earlier, is the force which is proportional to V, and I am going to write this as F equals minus K V, and I am going to call it drag force. K is the coefficient of drag. Minus sign again denotes that the force is opposite to the motion, and therefore the equation of motion is going to be mr double dot mass times acceleration equals F applied, that the force that I apply from outside, minus K V, which is the drag force. If I write these in component form, I get m x double dot equals F applied x component minus K x dot m y double dot equals F applied y component minus K y dot, and similarly m z double dot equals F applied z minus K z double dot. This is the simplest of drag forces, and in the next few examples we are going to see how to incorporate this in the motion. The first example I am going to take is going to be one dimensional motion without any applied force. There is no applied force, but drag is there. Therefore, initially I have to throw the particle with some initial speed v0, and as it moves along it experiences a force which is minus K V. V is changing with time, or I can also write V is changing with the distance. Let this direction be x direction, that is why I have written x here. The equation of motion for this is going to be m x double dot equals minus k x dot. In more familiar terms, it is going to be d over dt of x dot, which is nothing but x double dot, is equal to minus k over m x dot, or d over dt of x dot plus k over m x dot equal to 0. This is my equation of motion that I want to solve for this particle. You can check by direct substitution that the solution is going to be x dot as a function of time equal to some constant c e raised to minus k over m t. What is c? Let us write x dot at t is equal to 0, that is the initial time, I threw the particle with speed v0, and therefore I must have x dot at t equal to 0 is equal to v0, and when I substitute t equal to 0 here, I get this is equal to c, and therefore my general solution is going to be x dot, that is the velocity of the particle, equal to initial speed or initial velocity minus k over m t. Let us plot it and see how does it look. So initially the particle started moving with some speed v0, I am plotting vt versus t, and as time passed the velocity decreases exponentially. This curve is v0 e raised to minus k over m t. How about the distance travelled by the particle? That is also easy to calculate once I know the velocity. X dot t is given to be v0 e raised to minus k over m t. So the distance travelled in time t is going to be integral 0 to t x dot t prime dt prime, which is equal to v0 integral 0 to t e raised to minus k over m t prime dt prime. After integration I get xt is equal to v0 m over k 1 minus e raised to minus k over m t. So I have also calculated how much is the distance travelled in time t. As t goes to infinity, x goes to v0 m over k. So that is the distance that the particle will finally travel and stop after this. Let us see how does the plot of this look. If I plot xt as a function of time, initially obviously distance travelled is 0 and slowly it moves up and goes like this distance being v0 m over k. So let us look at this expression once more, which is v0 m over k 1 minus e raised to minus k over mt, and ask if this is the correct answer. One way to check this is let k go to 0 and I should get my familiar xt equals v0 t. But if I substitute k directly here, I get an answer like 0 over 0. which is not correct, I have to be more careful and take the limit k going to 0, keeping terms up to order k in this expression and see if I get the correct answer. If I do that, I find x is equal to V0 m over k, 1 minus 1 plus k over mt. This cancels and I get V0 t, which is correct. So this is one way when you get an expression in these, when you apply these forces, you can check your answer. Next, let us consider a particle still moving in one dimension, but applied on it is a constant force. So I have a particle, I apply a constant force F again in x direction, and let there be a drag force minus k v or minus k x dot, and I want to solve I want to see how this particle moves. The equation of motion is going to be mx double dot is equal to F minus kx dot. In this case, notice that I don't really have to start by shooting a particle with some initial speed. I can start with v t equal to 0, still 0. Because I am applying a force, the particle will start moving, and this is what I want to see, how the particle moves. So this is going to be one of my initial conditions. The other one is going to be, let us also say that x t equal to 0, it starts from the origin. If I rewrite the equation, it will come out in the form of x double dot is equal to F over m minus k over m x dot, or d over dt of x dot plus k over m of x dot is equal to F over m. Notice I have already solved this problem for F equals 0. That was one dimensional motion without any force. In such situations where I have one part like this and another part like this, I can write my solution as the previously obtained solution with F equals 0, which was nothing but c e raised to minus k over m t. This was x dot of t plus a particular solution that corresponds to the term on the right hand side. Remember, I am solving the equation d over dt x dot plus k over m x dot is equal to F over m. This is the solution corresponding to this part equal to 0. The particular solution would refer to this term, and you can see the particular solution is going to be x dot is equal to F over k. I substitute this here and I get on the right hand side F over m, and therefore my general solution for x dot is going to be x dot of t is equal to c e raised to minus k over m t plus F over k. This constant c is again determined by initial condition, which is nothing but initially the particle was at rest, and therefore I get c equals minus F over k, and the general solution therefore comes out to be x t. The solution with this initial condition comes out to be x dot t equals F over k 1 minus e raised to minus k over m t. Let us now look at this solution carefully. So I have x dot t equals F over k 1 minus e raised to minus k over m t. You notice as t goes to infinity, that is after a long time I have applied the force, x dot goes to F over k. This is nothing but the terminal speed. At this speed, the applied force F becomes equal to K times V terminal. The two forces balance, and therefore, the particle moves with a constant speed of V terminal. If I plot this speed, I am going to get Vt or x dot t, same thing, versus t. The final speed is F over K, and the speed slowly builds up. How about the distance traveled? Well, for that I again integrate it. So, I have x dot t equals dx dt is equal to F over K 1 minus e raised to minus K over m t. So, x at t is again going to be 0 to t F over K 1 minus e raised to minus K over m t prime dt prime. Integrating, I get F over K t minus m over K 1 minus e raised to minus K over m t. So, this is going to be the distance travelled by the particle. Now that we have gotten the expression for the distance travelled, let us play around with it a bit and see if it goes to correct limits. So, I have x t equals F over K t minus m over K 1 minus e raised to minus K over m t. So, first question I ask is, what happens if K goes to 0? Remember, I said earlier you have to be careful in taking limits. So, I am going to expand this term, keep terms up to order K and see what happens. In the limit of K going to 0, I can write 1 minus e raised to o minus K over m t. If K is really small for any t, I can write this approximately as 1 minus K over m t plus half K square t square over m square. Substituting this in here, I get x t is equal to F over K t minus m over K K over m t minus 1 half K square t square over m square, and expanding it further, I get x t equals F over K t minus t plus 1 half K over m t square, which is nothing but your familiar 1 half F over m t square, which is the correct answer in the limit of K going to 0. That is, I am taking a particle and applying a constant force F. Its acceleration is F over m, and then it moves distance 1 half F over m t square in time t. Let us try to plot this and see how it goes. So, x t was F over K t minus m over k 1 minus e raised to minus k over m t, again in the limit of very small t, basically making this term very small, we just saw that x t goes as 1/2 f over m t square. How about large t? In the large t limit, this term would tend to 0, and therefore, I would have x t as f over k t minus f m over k square. This is nothing but movement with a constant speed. F over k, you recall from earlier, is nothing but the terminal speed. So, the particle has now after a long time started moving with terminal speed f over k. So, therefore, if I combine the two and plot x t, is going to look like t x t. Initially, it is going as t square, and finally, it goes as a straight line with slope f over k, which is nothing but the terminal speed and which cuts the y axis somewhere here, which is nothing but f m over k square. So, this is how the particle is going to cover the distance with time. This is a problem where we applied a constant force. So, the most familiar problem in everyday life of this is a ball being thrown up with, say, some initial speed v0. The problem that I just solved, I took initial speed to be 0, but suppose I throw a ball up, then the force, and take this direction to be plus y, then the force applied is going to be minus mg, drag force is going to be minus k y dot, and the problem becomes similar to what I solved. I will leave this as an exercise to find how long does it take for the particle to reach up, how high does it go, because I am going to solve a slightly more complicated problem which is related to this, and that is going to be the motion in 2 dimension, the projectile motion in gravitational field. So, I am done with 1 dimensional motion now. Let us go to the 2 dimensional motion with drag force included. You are familiar with projectile motion which is in the vertical plane. In this motion, I take a particle and project it at some angle theta 0 from the horizontal with some initial speed v0, and without drag it follows a perfect parabola. And this problem you solved in your 12th grade. Height comes out to be v0 square sine square theta 0 over 2g. You can calculate the time, the range, and everything. What we are going to do now is make the problem slightly more complicated by including drag force in it in its simplest form. Therefore, my equation of motion for the projectile is going to be mx double dot is equal to minus k x dot, because there is no horizontal applied force, and in the y direction I am going to have my double dot is equal to minus mg minus ky dot. These are my 2 equations of motion when I am solving for a particle which is being thrown at an angle theta 0 with initial speed v 0. This I am taking to be positive y direction, this to be x direction. These two I have solved separately when I was solving the 1D problem, so that I know the solution. Mx double dot equals minus kx dot gives me x dot is equal to v initial, which in this case happens to be v 0 cosine of theta 0 e raised to minus k over m t, and also x as a function of time comes out to be v 0 cosine theta 0 m over k 1 minus e raised to minus k over m t. This is the motion in x direction, and this is related, this is going on concurrently with motion in y direction, for which I have m y double dot is equal to minus mg minus ky dot, or d over dt of y dot plus k over m y dot is equal to minus g. In our one dimensional example, we have already solved this with slightly different parameters. Instead of this minus g, I had an f there. The initial velocity was 0. Here initial velocity is v 0 sine theta 0. So, let us solve this. For that, as I said earlier, in the case of one dimension, the general solution is going to be summation of the particular solution and the solution of the homogeneous part, and therefore, y dot as a function of t is going to look like c e raised to minus k over m t minus mg over k, and c is determined by the initial condition, which is that y dot at t is equal to 0 is equal to v 0 sine of theta 0, and therefore, I have y dot of t is equal to v 0 sine of theta 0 plus m g over k e raised to minus k over m t minus m g over k, or I can also write this as y dot of t is equal to minus m g over k 1 minus e raised to minus k over m t plus v 0 sine theta 0 e raised to minus k over m t. This is how the velocity of particle in y direction varies with time. If I want to find the trajectory of the particle, that is, I want to find how does it go in the space, then I have to solve for x and y and plot them one y versus x, one versus the other. However, before we find the trajectory, let us play around with the expressions for the velocities that we have already obtained. X dot t is v 0 cosine of theta 0 e raised to minus k over m t, and we have just found that y dot t is equal to minus mg over k 1 minus e raised to minus k over m t plus v 0 sin theta 0 e raised to minus k over m t. At this point, I may ask, how long does it take time t before y dot becomes 0? That is, after I throw the particle, after I project the particle, when does it come to stop, or when does it reach its maximum height? So, for that I substitute this is equal to 0 and corresponding time would get me the answer. Let us do that. If I do that, I get mg over k 1 minus e raised to minus k over m t is equal to v 0 sin theta 0 e raised to minus k over m t, and this gives me v 0 sin theta 0 m v 0 sin theta 0 k over m g is equal to 1 minus e raised to minus k over m t over e raised to minus k over m t, or k v 0 sin theta 0 over m g is equal to e raised to k over m t minus 1, which implies e raised to k over m t is equal to 1 plus k v 0 sin theta 0 over m g, or time t when its velocity becomes 0 or reaches its highest point is equal to m over k log of 1 plus k v 0 sin theta 0 over m g. Let me again ask and check my answer. Is this correct in the limit of k going to 0? And sure it is, because t is equal to m over k log of 1 plus k v 0 sin theta 0 over m g. In the limit of very small k can be written as m over k expanding log, I get k v 0 sin of theta 0 over m g. This cancels, and I get my familiar answer v 0 sin theta 0 over g. After doing this exercise, let us go on to find the trajectory. For trajectory, what I will do is find x and y separately and plot them. Recall that without any drag force, one could eliminate t and find x and y, a direct relationship between x and y. This is not possible in this case. So, going back to our expressions, we had x dot t is equal to v naught cosine of theta 0 e raised to minus k over m t, which gives me x t is equal to m v 0 cosine of theta 0 over k 1 minus e raised to minus k over m t. This is my expression for x. You are also familiar with this from the earlier part of the lecture. Similarly, I have y dot t, which is nothing but minus mg over k 1 minus e raised to minus k over m t plus v 0 sine theta 0 e raised to minus k over m t. Integrating this, I get an expression for y as a function of time, and it comes out to be m v 0 sine theta 0 over k 1 minus e raised to minus k over m t minus mg over k t minus m over k 1 minus e raised to minus k over m t. You see, because t appears in linear form as well as this form, that is why I cannot eliminate it to get a direct expression between x and y. However, for a given time I can calculate x and y and plot the trajectory. If I do that for different k's and if fix v naught and sine theta naught, I find that for k equal to 0, it is a perfect parabola. However, as k is introduced, that means the drag force comes into play. Its height and range both start changing, and I will have got some numbers here which I will show you how for different parameters it changes. As an example of how the trajectories are affected for different values of drag coefficient or by this drag, I have taken a sample problem of a particle being thrown with a speed of 100 meters per second at an angle theta 0 equal to 45 degrees, and I will plot for 3 different k's the trajectories which I have calculated. I take k is equal to 0, which is the case of no drag or no viscosity. In that case, you are well familiar that this comes out as a parabola. Its height is about 254 meters and the range comes to about 1 kilometer, 1010 meters. Now I take k to be 0.1. The trajectory changes slightly. It goes, it comes down, but not as a parabola, but something like this. Its height now reduces to 175 meters and range comes out to be 495 meters. Notice that the reduction in height is about 20%, whereas the range has gone down by about 50%. If I go further and make k equals 0.2, the trajectory becomes even more like this, with height now becoming 135 meters and the range becoming 313 meters. Again, notice that the reduction in range is much more, which is about 40%, whereas the height goes down by about 20%. So, you see how introducing drag or this frictional force due to fluid or the gas affects the motion of a trajectory. This is a very important problem when we consider the motion of particles or motion of say bombs or motion of artillery pieces being thrown out, being projected in a battlefield. An interesting question you may ask at this point is, you all know from your 12th grade that if k is equal to 0, the maximum range which is attained is when theta is equal to 45 degrees. What theta for k not equal to 0? Is theta less than 45 degrees? Is theta greater than 45 degrees? The answer to this question is that theta should be slightly less than 45 degrees, because you saw that the height is not affected so much by introducing of k as the range. So, what I want to do is give slightly more of x component to the velocity if I want to fire the projectile farther and farther. The other way to look at the same problem is that when the particle is moving up, it spends more time because it is being pulled down by mg, it is also being pulled down by k Vy. It spends more time in going the same height than when it is coming down. So, in that time you want to cover as much distance as possible because x component of the velocity is also going down. So, to attain maximum range, I should fire at theta less than 45 degrees. So far I have considered the drag force, which is proportional to the velocity and in the opposite direction, and shown you through some examples how it affects the motion. This is the simplest possible drag force. As the speed increases, more dependence on velocity may come in the form of f may be equal to minus k v minus, let me write this k1, k2 v square, let us write a unit vector v so that it tells you this is opposite to the velocity vector, and higher order terms, this being the simplest. When these terms come into play, problem becomes non-linear, because now you have m r double dot is equal to f applied minus k r dot k1 r dot minus k2 r dot square r dot vector, and these are not easy to solve. In most of the cases you have to apply numerical methods to get the final solution. However, there are some cases where you can apply some techniques and get solutions. I will solve one example to illustrate this, and that would complete our lecture on drag forces. The example I take is that of F drag being proportional to v square, and obviously it is in direction opposite to its velocity. And I want to find, if I throw a particle up with some initial speed v initial, how long does it take to reach up? What is the height it can go up to? And what is the speed when it comes down? V final. Let us see what all answers can we get. If I write the equation of motion, since this is a one dimensional case, let me take y to be going up. I can write m y double dot is equal to minus mg minus k v square. This is when the particle is going up. Notice in this case I have to be careful when considering the motion of particle coming down. When the particle is coming down, I would have m y double dot is equal to minus mg plus kv square, because in that case the force, drag force, would be acting in upward direction. That is why I took this particular example. So, let us see how do we go about solving this. While the particle is moving up, I write my double dot equals minus mg minus k y dot square, and I go back to my technique of writing y double dot as d over dt y dot, which is same as d over dy y dot dy dt which is same as d over dy of y dot square 1/2. And therefore, I can write my equation as 1/2 d over dy y dot square is equal to minus mg over m minus k over m y dot square. And I have 1/2 d over dy y dot square is equal to minus g minus y dot square 1/2 d over dy y dot square plus y dot square equals minus g. I can solve for y dot square directly in terms of y. You see, I have eliminated time. So in this problem, it will not be possible for me to calculate how long does it take before the particle comes to stop, but I can certainly calculate how high the particle goes before it comes to stop. You can directly see that the solution of, I forgot a k over m here, so there is going to be a k over m here. Y dot square is going to be of the form c e raised to minus 2 k over m y minus m g over k. You can directly substitute this and then see, if I substitute y dot square with mg over k, it gives me minus g, and this satisfies the homogeneous part. Now to initial conditions. So I have y dot square equals some constant e raised to minus 2k over m y minus mg over k, and I know the initial velocity y dot square when y is 0 is equal to v initial square, and therefore v initial square is going to be equal to c minus mg over k, and that gives me y dot square is equal to vi square plus mg over k e raised to minus 2k upon m y minus mg over k. To find how high the particle went, I take y dot square to be 0 at y equal to h, and therefore I get vi square plus mg over k e raised to minus 2 k over m h equals mg over k, and that tells me that e raised to 2k over m h is equal to 1 plus vi square k upon mg, or 2k over m h equals log of 1 plus vi square k upon mg, or the height it went up to is equal to m over 2k log of 1 plus vi square k upon mg. This is the height at which it stops. Again, I will go back to limit of k going to 0 and see if my answer is correct. When the limit k equal to 0 is taken, I can expand the log term and write this as vi square k over mg, and therefore the height that I get is h equals m over 2k Vi square k over mg, which is our familiar result from your previous classes. So, I have calculated the height up to which the particle will go with the drag included. I will leave it for you as an exercise that when it comes back with velocity v final, then the relationship between v final and v initial square is going to be 1 over v final square plus k over mg is equal to 1 over v initial square. A word of caution though, when considering the motion of particle coming down, you should take proper account of the force of friction. The force of friction changes direction, and as showed in one of the previous slides, that you have to change the sign of the force. V final of course is going to be smaller than V initial, because in this friction the particle has lost energy. So, what we have done in this lecture is shown through some examples how the drag force affects the motion of a particle. I have considered the simplest possible form where F is proportional to the velocity itself, and another form where F is proportional to the velocity square. This is encountered when velocities are small and suffices in most of the cases. Another mathematical advantage or analytical advantage with this is that in most of the cases I can solve it analytically. If the speeds become higher, then higher orders of V's power come into play, and then one has to solve the problem numerically. With these, we finish the first part of these lectures on engineering mechanics. In this part, I have made you familiar with different coordinate systems that we use. Besides the x, y, z coordinate systems, Cartesian coordinate systems, we consider the planar polar coordinates r and phi. We considered cylindrical coordinates r, phi and z. We considered spherical coordinates r, theta and phi, and we used some of them while solving problems. Not only these coordinate systems are useful in solving mechanics problems, you will find them very useful in solving problems in electrodynamics and wherever there are certain symmetries. After this introduction to coordinate systems, we considered the motion of particles, single particles with constraints and learnt what are forces of constraints, what is free body diagram, how to take constraints into account, and how to solve problems when constraints are there. Following that, we considered a very special class of forces, or the frictional forces, and took them into account when solving dynamical problems. In these, we considered the regular frictional force that you are familiar with when one body slides over the other body, solid body, and we also considered the drag or viscous force in their simplest possible forms. One where F is proportional to the velocity, and also proportional to the v square. In the coming few lectures, we are now going to get more sophisticated, consider the work done by forces, do work energy theorem, and then go to many particle systems where we'll consider rigid body motion and things like those.